Okay, so I have detached that capacitor here to make it as fast as possible on triggering. I'm still having that decoupling cap over the voltage, and it takes power from this one. It's 5 volts, so there's no regulator here, so you can ignore all of this. It takes power directly in on this to here. So, and I have attached a switch so I can switch on and off the load as if it was the switch on the Commodore 64. And this is almost the same picture as I have on the C64. It's a bit different, but the reason for removing that capacitor was to see if I still got some blinking on that red LED even when I had this decoupling, and I do. It's very faint, but it's there, so I capture it with a scope. So let's have a look at that. So it's 500 microsecond per division and 2 volts per division. And I've been staring at this for a while, so let me just do this. Because the yellow one, that's the input, so it's connected to the input, and the output here is connected to red, that means green though. So this is input and this is output. So why do I get these drops and then it suddenly stabilizes? The thing is that when you attach a load, there will be a voltage drop, so that's no surprise. But why does it bounce up again to almost where it used to be? So, and I think what's happening here is that the contact, when you make contact, let me demonstrate. Let me demonstrate that for you. I couldn't find my my ball. So it's contact bouncing, I think. So when you make contact, then the actual contacts, they are bouncing, and it becomes more easier to see what happens if we move this output here upon the input. So I'll move it such that they when there's no load, they are the same. So we'll align it up here, so such that when there's no load, they are the same almost. So, and also let's increase the time base here, or decrease, such that it's faster, so we can scope it a little bit deeper. So let's find the first one. Yeah, that was the first one. So it has a lot of memory, this scope though, because it's a computer scope. Anyway, so let's set it to 1 there, 20 microsecond. So if I move it there, I can yeah, I can see that it's the same. It's the first pulse. So now we can see when there's no load, the voltages are almost the same. And then there's contact made, and therefore the voltage will drop. And the reason for that is because there's a long cable, and the voltage will drop, and also the voltage in the regulator of the power supply will also drop. And the yellow one here is the input, so you can see there's some difference here, and the reason for that is because there's some resistance inside here. I think this one is like 20 million, but you have contact resistance that can be between 10 and 100 microfarad, but I think it's more like 15. Or oh, wait. Yeah, 15 on minus and 15 on plus. That means 30, 60, and 80 total. So if there's like 1 ampere, there will be like 80 millivolt drop. But here it drops a lot more, so why does it drop that much? It's not like, if you look here, 0, 2 volt, 4 volt. Well, you have that capacitor there, and it's discharged. So, when that contact is made, this one has to be charged up, so charge from the power supply is then shared from the capacitors in the power supply. And this one, but this is so small so it doesn't matter, we'll have to charge this up, and there's a lot of current there instantaneously. And that's why you see this difference here between the input and the output though. So, but that's when the voltage has stabilized, you will see that they will come together though. So, and another thing you can notice is that, okay, so there's a lot of current going here, but then to me it looks like the contact is released again. So here you have the input again. So the contact is bouncing off such that it makes a spike. So because now the regulator in the power supply is now has compensated for this load, so it has much more voltage, and then it has to regulate down again to get to the right voltage again, and that produces a spike. And it's the same thing, but not as much as this in the Commodore 64 power supply. So, and here you can see the voltage on the output will drop even further, and that's not because of current, that's because the voltage protection is kicking in. So yeah, so now the contact is now bounced off, so for a while here there's no contact. So when you're scoping in like 20 microsecond, then this becomes very long. So, but it's not long at all, it's just that we are scoping it. So, and here you can see we are making contact again, but no, as before, it's not that big difference anymore. And why is that? Well, now this capacitor has some charge from the previous contact that was made before the contacts bounced off in here. So therefore the current isn't that large, but still there will be a spike when that bounces off again. And our protection circuit is now kicking in shortly, as you can see. So it's dropping. But why doesn't it drop all the way down? Well, I actually don't know. So, and then here there's no contact, and then you can see there's a contact again. Now they're very close together, both the input and the output, and suddenly you can see there's no more difference between the input and output. That means there's no more current going, or any significant current being shared between the capacitor in the power supply and the load. So, and here, for some reason, it's another bouncing off the contacts again in the switch, and then the protection circuit is once again kicking in here. So, and if there was contact at that moment, then you wouldn't see that drop as you could see here on the output, because then this one would have compensated for that. But since there's no connection anymore in here for that short moment, or this moment here, as you can see from here to here, therefore you will see this dip though. So, so, and here you see there's a contact made again, and let me just zoom it out a little bit. So it makes contact, bounces off, makes contact, bounces off, makes contact, bounces off, and here it stabilizes, it seems. And the regulator inside the power supply is now compensating for the new load, right? Because now it has to provide more power. And after a while you can see it stabilizes. So yeah, so if I zoom it out, you can see there's a drop here, chuk chuk chuk, because of the load that is introduced. Okay, so I have sent this saver out to several people, and one of them had a voltage that was 5.38 volts when it was unloaded. This doesn't mean that there's something wrong with the power supply. But anyway, it's below the threshold that I have in my saver. I found out that when you power on the switch of the Commodore, you get a spike. But first you get a dip. So let me redraw that. So you get a dip and there's some charging. And because of contact bounce, the contact is intermittently gone. So therefore you get a spike. And then it stays like this until next time you get contact. And then another spike, because it bounces off another time. It's these spikes that makes the voltage go above this threshold, so the saver is kicking in. And you would think that, okay, but the voltage is dropping down here again when there's no more power. And the problem is that there's another threshold here also, because we got hysteresis. So this 5.38 volts is above that lower threshold, so it will be stuck. If we're stuck in fault mode. So let me draw this. I have drawn this another time, so we will look at it again. So this is the input voltage, and then this is the output voltage. So this is in on the C64 Saver, and this is the output of the C64 Saver. So let's say we have 5 volt here, and 5.24, 5.42, and then let's say we have 10 volt or 12 volt for that matter on the input. So here the output is the same as the input, and when it reaches this upper limit, the output will then drop. That's what the saver is doing. But now, since we have hysteresis, it doesn't go on again when it drops below 5.42. It has to drop down to 5.24. And the thing is that this power supply, it sits inside this area. And therefore it can when the power supply then, or the saver kicks in, right? It cuts the outputs there, and therefore the power supply then will resort to the unloaded voltage, which is 5.38. So it will sit in here, it will never come down again and reset. So I think what I've done wrong with my circuits is that for those who have power supplies that are above 5.24, they will have a problem when the power is switched, or if the voltage is very close to this, they will get a fault immediately. So, and the equipment will not be damaged, but they can't use this saver. So, and I don't want so many returns. So what I've looked at is to increase this voltage, and we'll look at this in later videos, because I made more videos, but it was too long to put all of this in this video. So what I've done is that I have the lower voltage here and the higher here though. So 542 and 548 or something like that. So I have minimized this hysteresis, because here you have like 200 millivolt hysteresis, so I've reduced that to like 60 or 80, so maybe these figures aren't correct right now. Yeah, so that's what's happening. And of course I will change the values of the resistor, so people can use this as a saver, and it will be as safe as before. And the result is that I won't get so many returns, because there are power supplies out there that has much higher voltage. We can look at that also. That's something I've been thinking about showing in this video. So let's look at the voltage drop. So let's say this is a stretch. Call it a stretch. So this is distance, and on this distance you have let's put the PSU, or the power supply, on this side, the regulator, and you have a contact. So let's draw a contact, and it's open. So, yeah. And then you have a cable, so let's draw it like this, and then you have a contact again, or a solder point actually, and the MOSFET in the saver. So this is the saver, and then you have another contact in the yeah, you have a contact here also for the plug. There's a small cable here and a small cable there, and then you have the switch in the C64 with this, and this is the C64. So what happens to the voltage? So if you look at that, is this voltage, then if there's no load, then the voltage will be like 5 point, it depends on what kind of supply you have, and then you can have like 5.1. So if you have the power supply that is up at this level, when there's no load, it will be the same over the whole cable. There's no drop here. But if you attach a load, there will be some drop, and in particular in connections there will be more drop. But there will also be some drop over the cable, but not that much. And then solder joint, and then MOSFET a little bit more, 20 millivolt or something, at 1 amperes. And then finally the connector, that's also another drop. So you have a voltage that drops along these points like this. That's when you have a load, loaded, unloaded. The same happens for this 5.1 voltage supply, but it doesn't drop that much, because the thing is, so this is unloaded though, very poor drawing, but the thing is that when it's loaded, it is not dropping that much. The thing is that Commodore, they used a power supply with a thinner cable. I'm not sure if it was a longer cable, but I've heard that it was a thinner cable. So what they did, they upped the voltage to 5.3 to compensate for this drop. And what happens with my saver is that when this load is detached, the voltage goes into my hysteresis region, so that's not very good though. Yeah, so that was what I wanted to tell. So there are power supply there so that have a higher voltage, and it's not harmful in any way. So I have to change my thresholds.